And now in this lecture we will find out the radius of a circle using two different methods. In the domain we have a circle. We know that the center of the circle is at this point O. We also know that line segment AB equals to 6 units in its length, line segment BC equals to 15 units, line segment AD equals to 18 units in its length. We know that this angle BAD equals to 90 degrees, and this angle ABC is also equal to 90 degrees, and our mission is to find out the radius of this circle. So we start with the first method. We do a construction. From point C we draw perpendicular on AD. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD is E. So by doing this construction we created here quadrilateral ABEC. In this quadrilateral we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. And according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, the fourth angle must be also equal to 90 degrees. In order to complete the sum of the angles in this quadrilateral to 360 degrees, the fourth angle must be also equal to 90 degrees. So actually inside quadrilateral ABEC we have 4 right angles, and therefore quadrilateral ABEC is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other, that is to say AB equals to EC. But it is given as the question that AB equals to 6 units, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that BC equals to AE, but AE equals to 13, therefore no, BC equals to AE, but BC equals to 13 units, therefore AE must be also equal to 13 units. And what is the length of this line segment DE? For the domain it is very easy to see that DE equals to AD minus AE. That is to say, D equals to AD, that is 18, minus AE, that is 13. 18 minus 13 is 5, so DE equals to 5 units. In the next step, we will join points D and C together by a straight line. By joining points D and C, we created the green small triangle EDC. In the next step, we will implement the Pythagoras theorem on the green small triangle EDC. Here by PT is the progression for Pythagoras theorem. According to the Pythagoras theorem, in any triangle, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the green triangle is DC, therefore the square of the hypotenuse is DC squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to EC squared plus DE squared. Okay, it is equal to EC squared plus ED squared. So DC squared, that is the square of the hypotenuse, equals to EC squared. EC equals to 6 units, therefore EC squared equals to 6 squared, that is 36, plus ED squared. ED equals to 5, therefore ED squared equals to 5 squared, that is 25. In conclusion, we found out that DC squared equals to 36 plus 25. 36 plus 25 is 61. Here we take the root out of this equation and we get that DC equals to the square root of 61 units. The hypotenuse DC equals to the square root of 61 units. So I'll write it down in the drawing. In the next step, we will join points B and D together by a straight line. By joining points B and D, we created the right triangle ABD. This right triangle ABD. In the next step, we will implement the Pythagoras theorem on the right triangle ABD. Here by PT is the version for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABD is BD, therefore the square of the hypotenuse is BD squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to AB squared plus AD squared. So in conclusion, we found out that according to the Pythagoras theorem in the right triangle ABD, BD squared equals to AB squared plus AD squared. So BD squared, that is the square of the hypotenuse, equals to AB squared. AB equals to 6 units, therefore AB squared is 6 squared, that is 36, plus AD squared. AD equals to 18 units, therefore AD squared is 18 squared, that is 324. So BD squared equals to 36 plus 324, this is actually 360. We will substitute 360 by 36 times 10 and we will get that BD squared equals to 36 times 10. Here we'll take a root out of this equation. And we will get that BD equals to the square root of 36 times 10. The square root of 36, the square root of 36 is 6, so you can take 36 out of the root and you will get that BD equals to 6, and inside the root we have to leave 10. So if you know that the hypotenuse BD in the right triangle ABD equals to 6 times square root of 10 units. In the next step, we find out the area of triangle PDC. Okay. We find out the area of this green triangle, triangle BDC. Here the squared brackets is the sign for the area, it means the area of triangle BDC. The area of any triangle equals to the base of the triangle times the height to the base over 2. So we choose the base as BC. Times the height over 2. We substitute the base by 13 by BC times the height over 2. In the next step, we find out the height to the base. We must emphasize that the height to the base must create 90 degrees with the base. So we'll extend side BC by a straight line. And from point D, we'll draw perpendicular on the extended side BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees. According to our construction, we will define the touching point of the perpendicular from point D in the extended BC as F. Actually, DF is the height to the base, or the height to the extended base BC. Why? Because it creates 90 degrees with the extended base BC. Okay. So we'll focus on quadrilateral ABDF. Inside quadrilateral ABDF we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. And therefore quadrilateral ABDF that has 4 right angles, it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other, that is to say AB equals to DF. And it is given us the question that AB equals to 6 units, so we can write here that AB equals to 6. And from this equation 6 equals to AB equals to DF, we derive that DF it is also equals to 6 units. That is to say, the height equals to 6 units. Here the height is equal to df and it is equal to 6 units. Now we can easily find out the area of the green triangle, BDC. The area of the green triangle, BDC is equal to BC, the base is BC, and it is given us the question that BC equals to 13 units in its length, so we substitute BC by 13 times the height to the base. We just right now found out that the height to the base df equals to 6 units, so we substitute the height by 6 over 2. So the area of triangle BDC is equal to 6 over 2 is 3, and 3 times 13 is 39. So we found out that the area of the great triangle BDC equals to 39 square units. Okay. In the next step, I will present to you a new rule that will be actually rule number 1, and we will implement rule number 1 in our drawing. Rule number 1 is true in any circle, so the circle that I will draw could be any circle. The center of this circle is this point O. If triangle ABC is blocked by a circle, so inside this circle we have triangle ABC. It blocks, the circle blocks triangle ABC. This is triangle ABC. The length of side AB is equal to A units, side BC equals to B units in its length, and finally side AC equals to C units in its length. And we also know that the radius of this circle, OM, it is equal to capital R. So whenever you have a triangle that is blocked by a circle, Before I will continue, I will explain to you what is the meaning of a triangle that is blocked by a circle. Actually, only and only if all the three vertices of the triangle are touching the circle, then you can say that the triangle is blocked by a circle. Exactly as you can see in this drawing, you can see that this vertex is touching the circle at point A. This vertex of triangle ABC is touching the circle at point B. And finally, this vertex of the triangle is touching the circle at point C. Okay? So only if all the three vertices are touching the circle, you can say that the triangle is blocked by a circle. So if a triangle is blocked by a circle, then the following equation will be true. Then you actually can find the radius of this circle only by knowing the side lengths of the triangle and the area of the triangle. Okay? So the radius of this circle, we define the radius of this circle as capital R, will be equal to the multiplication of the side lengths of the triangle by each other, that is to say, will be equal to A times B times C over 4 times the area of this triangle ABC. Actually, you can implement this rule number 1 in our drawing. Why? Because in our drawing we have the green triangle BDC, but that is blocked by this circle. Why the green triangle is blocked by this circle? Because of the fact that this vertex touches the circle at point B. This vertex of the triangle BDC touches the circle at point C, and this vertex of the green triangle, touches the circle at point D. Therefore, we can definitely say that this green triangle is blocked by this circle. So I write it down. The green triangle BDC is blocked by a circle or by a circle, and therefore we can implement here rule number 1. We'll define the radius of this circle as capital R. Here OM equals to capital R. And according to rule number 1, we will get that the radius of this circle, capital R, is equal to the multiplication of the side lengths of the green triangle by each other. That is to say, it will be equal to BD times BC times DC over 4 times the area of the green triangle BDC. So the radius of this circle that blocks the great triangle BDC will be equal to BD equals to 6 times square root of 10 units times BC equals to 13 units times DC equals to the square root of 61 units over 4 times the area of this great triangle BDC that is blocked by the circle. We already found out that the area of the great triangle BDC is equal to 39 square units. And that is actually the answer to our question. In this question we ask to find out the radius of this circle, and the radius of this circle capital R equals to this expression. So in the next step we will just simplify this expression, and we finished with this question, or we finished with the first method of this question. Okay. Here we will divide both the numerator and the denominator of this expression by 13, and we get that capital R, the radius of this circle, is equal to square root of 61 times square root of 10 times 6. 13 over 13 is 1, so 13 will get cancelled, over 4 times 39, so we divide the denominator also by 13. 39 over 13 is 3. So the radius of this circle, capital R, equals to the square root of 61 times the square root of 10 times 6 over 4 times 3 is 12. Here we divide both the numerator and the denominator of this expression by 6, and we'll get that the radius of this circle capital R equals to the square root of 61 times the square root of 10, and 6 over 6 is 1, so 6 will get cancelled, over 12. 12 over 6 is 2. Here we have the algebraic identity that the square root of A times square root of B equals to the square root of A times B. We will use this algebraic identity in order to find out the value on square root of 61 times square root of 10. So according to this algebraic identity, the square root of 61 times the square root of 10 will be equal to the square root of 61 times 10, and all divided by 2. So the radius of this circle, capital R, equals to either the square root of 61 times 10 is 610 over 2 units, so in terms of numbers it is equal to 12.349 units. Finished with the first method. In the next step I will present to you the second method, to find out the radius of this circle. In the second method, in the first step, we will do all the things that we have already done in the first method. So I repeat on it quickly. From point C, we draw perpendicular on AD. So this angle equals to 90 degrees. And this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AD as E. So we have here quadrilateral ABEC that has 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Therefore quadrilateral ABEC is a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say AB equals to EC, but AB equals to 6, therefore EC will be also equal to 6. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that BC equals to AE, but BC equals to 13, therefore AE must be also equal to 13 units. And what is the length of line segment ED? The length of line segment ED is equal to AD minus AE. AD is 18, AE is 13, therefore AD minus AE is 18 minus 13, that is 5. So AD equals to 5 units. So until this stage, we have already done all the things that we did now in the first step. From now on, we'll continue with the second step. In the second step, we will do a construction, that is to say, from the center of this circle that is point O, we will draw perpendicular on chord BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees because it's our construction. We will define the touching point of the perpendicular from point O and chord BC, it's capital N. And we will define the touching point of the perpendicular from point O and AD as capital M. So, in the next step, I will present to you a new rule, and we will implement the new rule in our drawing. This will be actually rule number 2. Rule number 2 is true in any circle, so the circle that I will draw could be any circle. The center of this circle is at this point O. Here we have chord BC, that could be any chord. And from the center of this circle, that is to say from point O, we draw perpendicular on chord BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and code BC as M. According to this rule number 2, a perpendicular from the center of a circle, that is say point O, point O is the center of the circle, to any chord like in this drawing we have perpendicular OM towards chord BC. Bisect the chord. That is to say, perpendicular OM bisect chord BC. It means that BM equals to MC. BM equals to MC. So whenever you draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. That is actually rule number 2. We can actually implement rule number 2 in our drawing. Why? Because in our drawing we have the perpendicular ON from the center of the circle towards chord BC, and according to rule number 2, it bisects chord BC. That is to say, BN equals to NC. So I write it down. Now our original drawing, we have perpendicular ON, that is actually from the center of the circle, that is to say from point O to chord BC, and according to rule number 2, it bisects the chord, bisects the chord. That is to say, Bn equals to Nc. According to rule number 2. In the next step, we will focus on quadrilateral ABMN. Inside the upper quadrilateral ABMN, inside this quadrilateral ABMN, we have 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees. So, quadrilateral ABMN that has 4 right angles, we will relate to it as a rectangle. So I write it down. Quadrilateral ABMN is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, AM equals to BN. Likewise, we'll focus on quadrilateral, the lower quadrilateral MNEC. Inside this quadrilateral we have 1, 2, 3 rectangles. Therefore, this fourth angle must be also equal to 90 degrees. That is to say, quadrilateral MNEC that has 4 rectangles, it is a rectangle. I write it down. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, ME equals to NC. ME equals to NC. So we actually can summarize what we did until now. First of all, the first step, we found out that Bn equals to Nc according to rule number 2. Bn equals to Nc. In addition, we found out that Bn it is also equals to Am according to the rule that the opposite sides of a rectangle are equal to each other. So we can write here that Bn equals to Am, and according to the same rule that the opposite sides of a rectangle are equal to each other, we found out that NC equals to ME. So we can write here that NC equals to ME. And from this long equation, AM equals to Bn equals to NC equals to ME, we will derive that AM equals to ME. AM equals to ME. Here, side AM equals to side ME. In the next step, we will extend line segment DA until it touches the circle. We define the touching point of the extended line segment DA in the circle as point F. By doing this construction, we created a chord FD. And we drew perpendicular ON to chord BC. ON as a perpendicular, it is absolutely a straight line. So ON is a straight line. And if we focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees, rule number 1. So, we will focus on the upper side of ON at point M. According to rule number 1, the sum of the angles here must be equal to 180 degrees. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to rule number 1. So the missing angle must be equal to 90 degrees. Likewise, according to the same rule, rule number 1, if we focus on the lower side of the straight line ON at point M, here also the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the lower side of ON at point M. We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees. Therefore the missing angle here must be also equal to 90 degrees. So we actually found out that OM is actually perpendicular to chord FD. So I write it down. OM exists from the center of this circle, that is to say from point O. OM that exists from the center, line segment OM that exists from the center of this circle, that is to say from point O, is perpendicular to chord FD. That is to say, whenever you have on the center of the circle perpendicular to any chord, it will bisect the chord according to rule number 2. That is to say, we can conclude from it that perpendicular OM bisects chord FD. So OM is perpendicular to chord FD. Therefore, it bisects it. It bisects chord FD according to rule number 2. Okay. So, if chord FD is bisected by perpendicular OM, it means that FM equals to MD. FM equals to MD. Okay? But FM, it is actually also equals to FA plus AM. FA plus AM equals to FM. FA plus AM. So we substitute FM by FA plus AM, and this is equal, FM equals to MD. So MD equals to ME plus ED. MD equals to ME plus ED. So we substituted MD by ME plus ED. In conclusion, we found out that FA plus AM equals to ME plus ED. But we have already found out that AM equals to ME. Here, line segment AM equals to line segment ME. And because of the fact they are equal to each other, we can cancel them out. And we're left only with FA that is equal to ED. Here, line segment FA equals to line segment ED. But we have already found out that line segment ED equals to 5 units. So we can write here that ED equals to 5. And from this equation, FA equals to ED equals to 5, we will derive that FA equals to 5 units. In the next step, we will extend side BA by straight line until it touches the circle At this point, we define the dotting point of the extended side BA and the circle SP. And here you can implement the old rule number 2. Why? Because we have here two chords that are intersect with each other. That is to say, chord FD intersects with chord PB. According to old rule number 2, whenever we have two chords that intersect with each other, the following equation will be true. Here we have chord AB that intersects with chord CD at point O, therefore AO times OB equals to CO times OD. So as I mentioned, we can implement here the old rule number 2. Well, because we have here chord FD, we have two chords that intersect with each other. Chord FD, this is chord FD, that intersects with chord PB. Point A. Repeat again, in our original drawing, we have chord FD that intersects with chord PB at point A. Therefore, according to the old rule number 2, we get that FA times AD equals to PA times AB. Repeat again, FA times AD equals to PA times AB. According to the old rule number 2. FA equals to 5 units times AD equals to 8 units, and this is equal to PA. PA is the missing 9 segments, so we will leave it as it is, times AB. AB equals to 6 units, so we substitute AB by 6, and we found out that 5 times 18 equals to PA times 6. We will divide this equation by 6, and we get that PA equals to 5 times 18 over 6. So PA equals to 18 over 6 is 3, and 3 times 5 is 15. So we found out that the length of line segment P8 is equal to 15 units. Okay, P equals to 15 units. So in the next step, I will present to you a new rule, and we will implement the new rule in our drawing. So the new rule will be rule number 4. Usually rule number 4 states that if two chords are perpendicular to each other, then a certain formula will be true. We can actually find out the radius of the circle that contains the chord according to a special formula. So it is true for any circle, so this circle could be any circle. The center of this circle is at this point E. So we have two chords that are perpendicular to each other. We have chord AB is perpendicular to chord CD. That is to say, they create between them at the intersection point 90 degrees. We define the intersection point between the two chords as point O. So according to this rule number 4, if two chords, or if chord AB is perpendicular to chord CD and they are perpendicular to each other at point O, and we also know that the radius of this circle here, point E, is the center of the circle, therefore EM will be the radius of this circle that we will define as capital R. Then if we have two chords that are perpendicular to each other, then the following formula will be true. Actually, we can use the following formula in order to find out the radius of this circle that contains the two chords. The formula is as follows: 4r squared, r, capital R is the radius of this circle, EM equals to capital R, equals to AO squared plus OB squared plus CO squared plus OD squared. So because of the fact that in this drawing we have two chords that are perpendicular to each other, chord FB is perpendicular to chord CD, the following formula will be true. If the radius of this circle is capital R, then 4r squared equals to AO squared plus OB squared plus CO squared plus OD squared. So whenever you have two chords that are perpendicular to each other, you can use this formula in order to find out the radius of the circle that contains the two chords. Okay, and we can actually implement the new rule number 4 in our drawing. Why? Because in our drawing we have two chords that are perpendicular to each other. That is to say, chord FD is perpendicular to chord PB. For that reason, we can use rule number 4. So I write it down. We have chord FD that is perpendicular to chord PB. Therefore, we can use here rule number 4. And according to the code of the part is called FT is perpendicular to chord PB. Here, the create between them is the intersection point, that is to say point O 90 degrees. We can use the rule number 4. Here we define the radius of this circle OM as capital R, and the following formula will be 4. That's 4R squared, again R is the radius of this circle, will be equal to FA squared plus AD squared plus PA squared plus AB squared. Okay. 4R squared, R is the radius of the circle, will be equal to FA squared plus AD squared plus PA squared plus AB squared. Okay. So 4R squared equals to FA squared. FA equals to 5 units, therefore FA squared equals to 5 squared, it is 25. Plus AD squared, AD equals to 18 units, therefore AD squared equals to 18 squared, it is 324. Plus PA squared. PA equals to 15 units, therefore PA squared equals to 15 squared, that is 225, plus AB squared. AB equals to 6 units, therefore AB squared equals to 6 squared, that is 36. So in conclusion, we found out that 4R squared equals to 25 plus 225 is 250, plus 324 plus 36 is 360. So 4R squared equals to 250 plus 360. This is actually 610. Here we divide this equation by 4 and we get that R squared equals to 610 over 4. Here we take the root out of this equation and we get that R equals to the square root of 610 over 4. This is to say the radius of this circle that is equal to capital R is equal to the square root of 610 over square root of 4. Square root of 4 is 2. In conclusion, we found out that the radius of this circle equals to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. We finish with the second method. In the next step of the lecture, we start with the first method. So in the drawing we have a circle. The center of this circle is this point O. In addition we have line segment AB that is equal to 6 units. Line segment BC equals to 15 units in its length, and finally, line segment AD equals to 18 units in its length. We also know that this angle BAD equals to 90 degrees, and this angle ABC is also equal to 90 degrees. Our mission is to find out the radius of this figure that we define as capital R, or the length of OM that is equal to capital R, according to our definition. So, in the first step, we did a construction, that is to say, from point C, we draw perpendicular on AD. So this angle equals 90 degrees, and this angle equals 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD as E. By doing this construction, we created quadrilateral ABEC. Quadrilateral ABEC has 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Therefore quadrilateral ABC is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC, but AB equals to 6 units, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that BC equals to AE. But BC equals to 13 units, therefore AE must be also equal to 13 units. What is the value of ED? ED equals to AD minus AE. That is to say, ED equals to AD, that is 18, minus AE, that is 13. AD minus AE is 18 minus 13, that is 5. So we found out that ED equals to 5 units. Okay. Then we join points C and C together by a straight line. By joining points C and C, we created the green small triangle EDC. Then we implemented the Pythagoras theorem on the right green small triangle EDC. Here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendicular. The hypotenuse in the green small triangle is DC, therefore the square of the hypotenuse is DC square, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to EC square plus ED square. Okay, so in conclusion, we found out that according to the Pythagoras theorem, DC square equals to EC square plus ED square. Here EC equals to 6, therefore EC square is 6 squared, that is 36. Plus ED square. ED equals to 5 units, therefore ED square equals to 5 squared, that is 25. In conclusion, we found out that DC square equals to 36 plus 25. 36 plus 25 is 61, so we found out that DC square equals to 61. We took the root out of this equation and found out that DC equals to the square root of 61 units. Yeah. DC, the hypotenuse DC equals to the square root of 61 units. In the next step, we join points B and D together by a straight line. By joining points B and D, we created the right triangle ABD. Then we implemented the Pythagoras theorem on this right triangle ABD. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is BD, therefore the square of the hypotenuse is BD squared, and it must be equal to the sum of the squares of the perpendiculars. This is to say, it must be equal to AB squared plus AD squared. So in conclusion, we found out that in the right triangle ABD, according to the Pythagoras theorem, BD squared equals to AB squared plus AD squared. So BD squared, that is the square of the hypotenuse of the right triangle ABD, equals to AB squared. AB equals to 6, so AB squared equals to 6 squared, that is 36, plus AD squared. AD equals to 18, therefore AD squared equals to 18 squared, that is 324. In conclusion, we found out that BD squared equals to 36 plus 324. 36 plus 324 is 360. So we found out that BD square equals to 360. Then we substituted 360 by 36 times 10. And then we took a root out of this equation. And we found out that BD equals to the square root of 36 times 10. Then we took 36 out of the root, because the square root of 36 is 6. Inside the root we left only the square root of 10. So we concluded and found out that BD the hypotenuse of the right triangle ABD, it is equal to 6 times square root of 10 units. In the next step, we calculated the area of the main triangle BDC. The area of main triangle, and especially the area of triangle BDC, equals to the base of the triangle times the height to the base over 2. Here, the height to the base must create 90 degrees with the base. Okay, so the area of the mid triangle BDC equals to the base of the triangle. We choose the base as BC, so we substitute the base by BC times the height over 2. Okay. In order to find out the height of the green triangle BDC, we did the construction. We extended side BC by a straight line, and from point D we drew perpendicular on the extended side BC. We defined the touching point of the perpendicular from point D and the extended BC as F. So in this way we created quadrilateral ABDF. Inside quadrilateral ABDF we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. Therefore quadrilateral ABDF is a rectangle. Quadrilateral ABDF is a rectangle, but we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side DF. And it is given us the equation that AB equals to 6. Here, first of all, AB equals to DF. According to the rule that the opposite sides of a rectangle are equal to each other, it is given us the equation that AB equals to 6 units. And from this equation, 6 equals to AB equals to DF. We derive that DF is also equals to 6 units. DF equals to 6 units. Therefore, DF it is also the height. So the height to the base of the green triangle BDC equals to 6 units. Now we can easily find out the area of the green triangle BDC. The area of the green triangle BDC equals to the base, that is BC, times the height over 2. But BC equals to 13, therefore we substitute BC by 13 times the height. We just right now found out that the height equals to 6 units, so we substituted the height by 6, all divided by 2. So the area of triangle, the green triangle BDC equals to 6 over 2 is 3, and 3 times 13 is 39. So we found out that the area of the green triangle BDC equals to 39 square units. Okay, then I presented to you a new rule, and we implemented the new rule in our drawing. According to the new rule, it is actually rule number 1. If triangle ABC is blocked by a circle, this is triangle ABC that could be any circle. Triangle ABC is blocked by this circle. Note that the radius of this circle OM equals to capital R, and the length of side AB of the triangle ABC is A units, the length of side BC is B units, and the length of side AC is C units. Then, whenever you have a triangle that is blocked by a circle, then you can know the radius of this circle that blocks the triangle according to the following formula. that the radius of this circle that blocks triangle ABC, that could be any triangle, it is equal to A times B times C, that is the multiplication of the side lengths of the triangle by each other, over 4 times the area of this triangle, triangle ABC. Okay, we can actually, before that, the definition of a triangle that is blocked by a circle is, it means that all the three vertices are touching the circle, like you see in the drawing. So we can actually implement rule number 1 in our drawing. Why? Because in our drawing we have the great triangle BDC. This vertex touches the circle at point B. This vertex touches the circle at point C, and this vertex touches the circle at point D. Therefore, we can definitely say that the great triangle BDC is blocked by this circle. Therefore, we can implement here rule number 1. I repeat again, the great triangle BDC is blocked by a circle. Therefore, according to rule number 1, the radius of this circle that blocks the great triangle BDC will be equal to the multiplication of the side lengths of the triangle by each other. That is to say, it must be equal to BC times C, BC times CD times BD. Okay. This is BD times BC times DC over 4 times the area of the great triangle, triangle BDC. Over 4 times of the great triangle, triangle BDC, the area of the great triangle BDC. But we have already found out that the area of the great triangle BDC equals to 39 units. So actually found out that it is actually also the answer to the question, that the radius of this circle, the capital R, equals to this expression. In the next step, we simplify this expression. That is to say, we divided both the numerator and the denominator of this expression by 13. So in the numerator we have 13, it's 13 over 13 is 1, so we left only with C square root of 61 times square root of 10 times 6 over 4 times 39. We multiply the denominator by 13 also. 39 over 13 is 3. So in total, in the denominator we have 4 times 3, that is 12. Okay. So the radius of the circle equals to the square root of 61 times square root of 10 times 6 over the radius of this circle equals to the square root of 61 times square root of 10 times 6 over 12. Here we divided both the numerator and the denominator of this expression by 6. 6 over 6 is 1, so in the numerator we left only the square root of 61 times square root of 10 over 12 over 2 is 6. Okay. In the next step, we use the algebraic identity that the square root of A times square root of B equals to the square root of A times B. Therefore, according to this algebraic identity, the square root of 61 times square root of 10 will be equal to the square root of 61 times 10, all divided by 2. And 61 times 10 is 610, so I found out that the radius of this circle is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. So we finish with the first method. In the next step, I presented to you the second method to find out the radius of this circle. In the second method, in the first step, we did all the things that we have already done in the first method. That is to say, from point C we draw perpendicular on AD. This angle equals to 90 degrees, this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD as E. So here we have quadrilateral ABEC. Inside this quadrilateral we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees, therefore quadrilateral ABEC is a rectangle and the opposite sides of a rectangle are equal to each other. That is to say AB equals to EC, but AB equals to 6, therefore EC must be also equal to 6 units. According to the same rule that the opposite sides of a rectangle are equal to each other, we get that BC equals to AE. But BC equals to 13, therefore AE must be also equal to 13. And what is the value of ED? ED equals to AD minus AE, that is to say it is 18 minus 13, that is 5. So until now we did all the things that we have already done in the first method, then from now on we continue according to the second method. So from point O we draw perpendicular on chord BC. That is to say this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. And we define the touching point of the perpendicular from point O and chord BC as capital N. And we find the touching point of the perpendicular from point O and AD as M. Then I presented to you a new rule and we implemented the new rule in our drawing. According to rule number 2, whenever you have a perpendicular from the center of a circle to a chord, it will bisect the chord. So from the center of the circle we have perpendicular OM. And according to this rule, rule number 2, perpendicular ON towards chord BC bisect chord BC. That is to say, BM equals to MC. We can actually implement rule number 1 in our drawing. Why? Because in our drawing we have from the center of the circle, that is to say from point O, we have perpendicular ON on chord BC. Therefore, according to rule number 2, we get that BN equals to NC. Okay, repeat again, perpendicular ON to chord BC bisect chord BC according to rule number 2. That is to say, BN equals to NC. Okay, then we focused on quadrilateral ABMN. Inside this quadrilateral we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees, therefore quadrilateral ABMN is a rectangle. Quadrilateral ABMN is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, NC equals to ME. That is to say, BN equals to AM. BN equals to AM. Likewise, we focus on the lower quadrilateral MNEC. In the lower quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral MNEC is a rectangle because it has 4 right angles. And you know that the opposite sides of a rectangle are equal to each other. That is to say, NC equals to ME. Again, quadrilateral MNEC is a rectangle, and in quadrilateral MNEC, ME equals to NC. So we can summarize what we did until now. Coming to rule number 2, we already found out that BN equals to NC. But according to the rule that the opposite sides of a rectangle are equal to each other, we also know that BN is also equals to that AM equals to BN. that Bn equals to Am. So we can write here that Bn equals to Am, according to the rule that the opposite sides of a rectangle are equal to each other. Likewise, according to the same rule, we concluded that NC equals to ME. So we can write here that NC equals to ME, and from this equation AM equals to BN equals to NC equals to ME, we will derive that AM equals to ME. AM equals to ME. Here, side AM equals to side ME. Okay. Then, in the next step, we extended line segment DA until it touches the circle at point F. By doing this construction, we get it called FD. And here, we have ON is perpendicular to chord BC. ON is perpendicular, it must be a straight line. So if you focus on the upper side of the straight line, ON at this point M, according to rule number 1, the sum of the angles from one side of the straight line is equal to 180 degrees. So at the upper side of ON at point M, the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees according to rule number 1. Therefore this missing angle must be equal to 90 degrees. Likewise, we focus on the lower side of the straight line ON at point M. Here also, the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the lower side of ON at point M? We have this angle that is equal to 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees according to rule number 1. Therefore, this missing angle must be also equal to 90 degrees. So I actually found out that OM is perpendicular to chord FD. And point O is the center of the circle. And whenever from the center of the circle we are perpendicular to chord, it bisects the chord. That is to say, FM equals to MD. So I repeat on it here. We found out that OM is perpendicular to chord FD. Why? Because this angle equals to 90 degrees and this angle equals to 90 degrees. Therefore, OM is perpendicular to chord FD. Therefore, according to rule number 2, OM bisects chord FD. That is to say, FM equals to MD. Okay. Therefore, it bisects chord FD. According to rule number 2, that is to say, FM equals to MD. FM, it is actually equals to FA plus AM. So you can substitute FM by FA plus AM, and it is equal to MD. MD, it is equal to ME plus ED. So you can substitute MD by ME plus ED. So if we found out that FA plus AM equals to ME plus ED. But we have already found out that AM equals to ME. Here, AM equals to ME. So we can cancel the two line segments that are equal to each other. We can cancel them out, and we left only with FA that is equal to ED. Here, chord FA is equal to chord ED. But we have already found out that ED equals to 5 units, so we can write here that ED equals to 5. And from this equation, FA equals to ED equals to 5, we will derive that FA is also equals to 5 units. Here, FA is also equals to 5 units. Okay. So, in the next step, I reminded you the old Before that, we extended side BA by a straight line until it touches the circle at point P. Okay, so we have here chord FD that intersects with chord BP at point A. And according to the old rule number 2, whenever you have two chords that intersect with each other, yeah, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement rule number 2 in our drawing. Why? Because in our drawing we have chord FD that intersects with chord PB at point A. Repeat again. In our original drawing we have chord FD that intersects with chord PB at point A. Therefore, we can implement here the old rule number 2. According to the old rule number 2, we will get that FA times AD equals to PA times AB. According to the old rule number 2, FA times AD equals to PA times AB. Okay? And FA equals to 5 units, AD equals to 18 units. PA is the missing line segment, so we leave it as it is, and AB equals to 6 units, which is 5 times 18 times PA times 6. Here we divided this equation by 6 and found out that PA equals to 5 times 18 over 6. 18 over 6 is 3, and 3 times 5 is 15. So we found out that the missing line segment PA equals to 15 units in its length. So in the next step, I presented to you a new rule number 4, and we implemented rule number 4 in our drawing. Rule number 4 states that whenever you have two chords that are perpendicular to each other, then the certain formula is true. So in this drawing we have chord AB that is perpendicular to chord CD. They are perpendicular to each other at point O. Why? Because they create 90 degrees at the intersection point O. And we know that the radius of this circle is equal to capital R, EM equals to capital R. So whenever you have two chords that are perpendicular to each other, then the following equation will be true. 4R squared, R is the radius of this circle that contains the two chords, equals to AO squared plus OB squared plus CO squared plus OD squared. Again, 4R squared equals to AO squared plus OB squared plus CO squared plus OD squared. We can actually implement rule number 4 in our drawing. Why? Because of the fact that in our drawing we have also two chords that are perpendicular to each other. Here chord FD is perpendicular to chord PB at point A. At point A they create between them 90 degrees. Therefore they are perpendicular to each other. For that reason you can implement here rule number 4. I repeat again. In our original drawing we have chord FD that is perpendicular to chord PB. Therefore, we can implement here rule number 4, and according to rule number 4, because of the fact that chord BB is perpendicular to chord FD, we'll get that 4 times R squared, R is the radius of this circle, equals to FA squared plus AD squared plus PB squared plus AB squared. Again, 4 times R squared equals to FA squared plus AD squared plus PA squared plus AB squared. So 4 times R squared, R is the radius of the circle, equals to FA squared. FA equals to 5, therefore FA squared equals to 5 squared, that is 25, plus AD squared. AD equals to 18, therefore AD squared equals to 18 squared, that is 324, plus PA squared. PA equals to 15, therefore PA squared equals to 15 squared, that is 225. plus AB squared. AB equals to 6 units, therefore AB squared equals to 6 squared, that is 36. So in conclusion, we found out that 4r squared equals to 25 plus 225 is 250, plus 324 plus 36 is 360. So 4r squared equals to 450 plus 360. 250 plus 360 is 610. So in conclusion, we found out that 4r squared equals to 610. Here we divided this equation by 4 and we found out that r squared equals to 610 over 4. Here we took a root out of this equation and we found out that r equals to the square root of 610 over 4. That is to say, r equals to the square root of 610 and the square root of 4 is 2. So in conclusion, we found out that the radius of this circle, that is to say OM, that is equal to capital R according to our definition, the radius of this circle equals to either square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. Okay, thank you very much.